Okay. Okay, this is West Nile virus. I actually didn't mean to go this one, but this one will do okay. There's actually a more interesting one. Pardon me if I just go and try to obtain that one. This one that exhibits more visual dynamics of interest. Oh, come on. Hello. What am I doing here? Boom. Okay. Yeah. Okay. So, hello. Wait, why aren't we closing down? Hello. Okay. So what's up with this? Let's close the window. Did I close my other AnyLogic window? I'm setting kill. Looks like AnyLogic may have died out. Okay, coming back into it. Hello? Where's my AnyLogic? Okay. Okay, is AnyLogic even running? Grab AnyLogic. AnyLogic is there. Okay, I'm gonna kill it and restart it. Kill 1916 927 boom 928 boom. Okay, now let's see if it's running. Boom. No. Okay. Now we may be okay. I don't know where it went there. Okay. Great. Well, that's interesting. My recorder also disappeared. Okay. So let's go record that again. Boom. So sorry. Okay, great. So I was going to show a simple gridded model. So gridded, there it is. Okay. Great. Okay, so I'll show this. Well, let me get this recording. It is. Okay, so let me first show the dynamics associated with this model. This model uses the same basic paradigm. Well, that's less. That's not the one I actually wanted, but okay. Sorry, I'm just gonna open another one that may be the correct one. Sorry about that. Okay, yeah. Okay, yes. Okay, here we go. Yes. Okay, right. No, this was, okay. Well, basically, this model makes use of the same basic mechanisms in the sense that you have a set of grid squares. Each grid square is associated with dynamics described by a set of stocks and flows. I'm going to actually show this one because they're a little bit prettier and easier to understand. In this model, we have these individual squares, and the squares are connected with their neighbors, so there's coupling. between them at the level of the system dynamics. So if we go look at a given patch, the given patch's dynamics are described by a very simple process involving migration, maturation, endogenously, and deaths. So we have a number of individuals in this patch. Individuals can migrate in or out, and there's maturation of individuals, there's birth of individuals in this patch, and then they start immature and they get to a mature phase where they can reproduce. And they all can die off, the assumption being that die-off occurs in adulthood rather than in the earliest stages here. The net migration here is dictated by the relative sizes of those populations. So there's a function here, and get net immigration rate, and basically there's a diffusion process. So we go over all neighbors, and we have a net migration rate that's given by some diffusion coefficient times the difference between our total number of mature individuals and the one in the neighboring patch, that neighboring patch. And so if the neighboring patch has a larger number than us, this will be positive and will tend to have ones coming in. Otherwise, it will tend to be going out. And so, in other words, we have this kind of maturation and diffusion of these individuals throughout this entire model. If we have a large number here, it'll tend to start to spread to other nearby patches for the immediately adjacent patches. And if you run this out over time, you can get interesting dynamics associated with it, whereby there are these kind of waves of migration that sweep through and so on. So once again, we have patches here whose dynamics are described by stocks and flows, and they move. This is another type of agent-based model. Same basic principle, except that we have it applied spatially rather, as the previous CTL one. This is applied spatially rather than applied according to networks. Okay, let's take a look at a different sort of model, though, which makes use of this. One would be, there's a model for health economics here. There's a basic health economics model here. And yes, I'm going to close that. Okay. I should stop the recording.